Right now, somewhere on Earth, a dish the size of a football field is pointed at an empty patch of sky, listening for a signal that takes over 20 hours to arrive. The thing sending it is 15 billion miles away. It was built in the 1970s. And this year, on purpose, NASA is turning parts of it off. It's called Voyager 1. NASA built it to last 5 years. It has been running for 49. It has survived a 1970s chip failure nobody alive today knew how to fix at first. It has crossed a boundary no human-made object had ever crossed. And its power source is dying on a schedule nobody can stop. This is the story of the two machines that outlived everyone who built them and the slow, deliberate way NASA is now saying goodbye. You're watching Mindwired. This is the story of Voyager 1 and Voyager 2, built for a 5-year mission, still flying after 49 years, and now, one instrument at a time, going quiet. Chapter 1, the machine that was never supposed to see this year. In 1965, an MIT graduate student noticed something strange. Around the year 1977, Jupiter, Saturn, Uranus, and Neptune would line up in a way that let a single spacecraft visit all four, using each planet's own gravity as a slingshot to the next. That alignment happens roughly once every 175 years. NASA called the idea the Grand Tour. In January of 1972, the Grand Tour was cancelled. The money went to the space shuttle instead. What survived was a smaller, cheaper version. 2 identical spacecraft aimed at just 2 planets, Jupiter and Saturn. NASA called it Mariner Jupiter-Saturn 77. Even that cheaper version wasn't a sure thing. JPL brought 3 different budget options to Congress in early 1972, ranging from about $210 million up to $320 million. On March 7th, 1977, months before launch, NASA's administrator renamed the mission. Mariner Jupiter-Saturn became Voyager. One man would stay with this mission for the rest of his career. Ed Stone became Voyager's project scientist in 1972, and he was still its project scientist 50 years later in 2022. 50 years, one person, one job. He died in June of 2024 at 88, having outlived almost every deadline anyone ever set for this mission. Here is the number that matters most. NASA's own mission documents say it plainly. The spacecraft were built to last 5 years, long enough to reach Jupiter and Saturn, and nothing more. Nobody designing it in 1977 expected anyone to still be listening to it in 2026. Confusingly, Voyager 2 left Earth first on August 20th, 1977. Voyager 1 launched second on September 5th on a faster, more direct path that would let it arrive at Jupiter months earlier. Both rode Titan 3E Centaur rockets off the same launch pad in Cape Canaveral, Florida, 3 weeks apart. The two spacecraft weren't just similar. They were identical twins, built side by side, so that if one failed outright, the other could still complete the mission alone. That backup plan is exactly what ended up happening, just not the way anyone expected. Both machines survived. It's the plan itself that eventually had to change. Almost nobody talks about how close Voyager 1 came to never leaving the atmosphere at all. During its own launch, the Titan rocket's first stage burned an off-ratio fuel mixture and shut down early. The Centaur upper stage had to compensate, burning harder than planned to make up the difference. By the time Voyager 1 reached a stable trajectory, the Centaur stage had roughly 3.5 seconds of fuel left. 3.5 seconds. That was the entire margin between the most photographed spacecraft in NASA's history and a mission that ends on the launch pad. Inside both spacecraft sat 6 computers in 3 redundant pairs, running on a combined clock speed of about 8,000 instructions per second. NASA has run its own comparison. A single smartphone from 2013 could process over 14 billion instructions per second. That's not a difference in years. That's a difference in kind. Power for both spacecraft comes from 3 plutonium generators each, converting the heat of radioactive decay directly into electricity. At launch, that produced about 470 watts, barely enough to run a couple of hairdryers. That decay never stops, and it never reverses. Every year, both spacecraft have a little less power than the year before, permanently. That single fact is the reason this whole story exists. To put 470 watts in perspective, that's roughly what it takes to run 4 or 5 ordinary household light bulbs. An entire spacecraft, 15 billion miles from the nearest wall outlet, running on about as much power as your living room lamp. Chapter 2. The accident that became a discovery. On March 5th, 1979, Voyager 1 made its closest approach to Jupiter, passing within about 350,000 kilometers of the cloud tops. It took almost 19,000 pictures of the Jupiter system and found something nobody had confirmed before. Jupiter has its own faint ring. 2 NASA probes, Pioneer 10 and 11, had already flown past Jupiter earlier in the decade, but their cameras were far simpler. Next to Voyager's pictures, Pioneer's looked like rough sketches. Voyager 1's images are also credited with turning up 2 more small moons hiding close to Jupiter itself, later named Metis and Thebe. But the discovery that mattered most almost didn't happen on purpose at all. 4 days after the flyby, a JPL navigation engineer named Linda Morabito was doing routine work, enhancing a picture of Jupiter's moon Io, just to pick out faint background stars for tracking the spacecraft's position. On the edge of Io, she saw something that shouldn't have been there. An umbrella-shaped cloud rising roughly 270 kilometers off the moon's surface. Her team spent the rest of that day ruling out every boring explanation. A camera glitch, an undiscovered moon passing behind Io, none of it fit. What she'd actually found was an active volcano erupting on another world. It was later named Pele. It was the first time anyone had ever seen active volcanism happening anywhere but Earth. By the time scientists finished reviewing Voyager 1's full image set of Io, they'd found 8 active plumes, not 1. A woman doing routine navigation math, looking for background stars, had just proven that Earth wasn't the only geologically alive world in the solar system. Planetary scientists have been teaching that discovery, and the way it happened, to every generation of students who came after her. Voyager 1's cameras also caught Jupiter's Great Red Spot as something dynamic for the first time, a storm large enough to swallow Earth, rotating counterclockwise, tangled up with smaller storms feeding in and out of it. Jupiter had just stopped being a picture in a textbook and started being a place with weather. And Jupiter was only the first stop. Both spacecraft still had a much longer road ahead, and one of them was about to make a choice that would end its journey early. Chapter 3. The moon that cost a planet. On November 12th, 1980, Voyager 1 reached Saturn, passing about 124,000 kilometers from the planet. It found strange radial spoke patterns moving through Saturn's rings, 5 new moons, and a level of structure in the rings nobody had modeled before. But mission planners had a decision to make, and it came down to one moon, Titan. Titan had a thick atmosphere, mostly nitrogen, so dense that Voyager's cameras couldn't see through it to the surface at all. That single, frustrating, opaque haze is exactly why later missions went back with radar instead of cameras. Voyager didn't just study Titan. It's the reason anyone thought Titan was worth another trip at all. Engineers had studied more than 10,000 possible trajectories. A close pass by Titan to study that atmosphere properly and a path onward to Uranus were mutually exclusive. Voyager 1 could only do one. NASA chose Titan. The flyby bent Voyager 1's path permanently out of the plane the planet's orbit in. It would never encounter another planet again. Voyager 1's entire future beyond Saturn was traded for one close look at a single moon's clouds. Voyager 2 had been launched on a different path, specifically to keep the door to Uranus and Neptune open. Now it would have to make that journey alone. On August 25th, 1981, Voyager 2 made its own pass by Saturn. And about 100 minutes after closest approach, something on board seized up. The gearing that aimed its camera platform jammed, from a lubrication failure identical to one that had already hit Voyager 1 at Jupiter. For several days, Voyager 2 couldn't reliably point its own cameras. Engineers 1,500 million kilometers away had to diagnose and fix a mechanical jam on a machine they could not touch, without losing the one trajectory that still led to 2 undiscovered planets. By August 28th, 3 days later, they had it working again. The path to Uranus and Neptune was still open. One spacecraft's journey had just ended at Saturn. The other's was about to go somewhere no machine, before or since, has ever gone. Chapter 4. The Only Spacecraft. On January 24th, 1986, Voyager 2 flew within about 81,000 kilometers of Uranus's cloud tops. It found 11 new moons, 2 new rings, and something genuinely strange. Uranus's magnetic field is tilted about 59 degrees off its spin axis and isn't even centered on the planet. No other planet studied works quite like that. As of today, in 2026, no other spacecraft has ever been back to check. 3.5 years later, on August 25th, 1989, Voyager 2 reached Neptune, coming within about 4,800 kilometers of the clouds. It remains the closest planetary approach of the entire mission. That night, JPL turned its own TV studio into Neptune Mission Control. Engineers crowded around monitors, watching pictures arrive after a 4-hour trip at the speed of light. What came back was a storm called the Great Dark Spot, with winds measured at over 2,000 kilometers an hour, the fastest ever recorded anywhere in the solar system. And then there was Triton, Neptune's largest moon, one of the coldest surfaces ever measured in the solar system, at about minus 235 degrees Celsius. It should have been dead. Instead, Voyager 2 found active nitrogen geysers, dark plumes climbing 8 kilometers into the sky, drifting 150 kilometers downwind before settling. The morning after the encounter, the sitting Vice President of the United States showed up at JPL personally to congratulate the team. As of this year, Voyager 2 remains the only spacecraft in history to have ever flown past either Uranus or Neptune. NASA has a concept for a future mission to Uranus. It has no approved launch date and realistically wouldn't arrive until sometime in the 2030s at the earliest. For Neptune, there isn't even a concept. No mission of any kind is currently planned. For at least another decade, and possibly longer, everything humanity knows firsthand about 2 entire planets still comes from one spacecraft's single pass in the 1980s. The Grand Tour was over, but for both spacecraft, the most human part of the mission hadn't happened yet. Chapter 5. The message that will never arrive. Before either spacecraft launched, NASA gave a small committee an unusual assignment: build a message for whoever might find it, someday, out there. The committee was chaired by astronomer Carl Sagan. Alongside him, Frank Drake, artist John Lomberg, music producer Timothy Ferris, and a young writer named Anne Druyan. On June 3rd, 1977, 2 days after Sagan and Druyan privately told each other they were in love, Druyan sat down and recorded her own brainwaves and heartbeat to be encoded onto the record. She was thinking about him the whole time. Neither of them knew yet whether the record would even be approved. It was days later. What they built was a 12-inch, gold-plated copper disc packed with a needle and cartridge to play it, sealed in a protective aluminum jacket. On it, 115 images of Earth and its life, spoken greetings in 55 languages, opening with Akkadian, a language 6,000 years dead, and closing with a dialect of Chinese. And 90 minutes of music. Bach, Mozart, Beethoven, Chuck Berry's Johnny B. Good, a blues recording by Blind Willie Johnson made in the 1920s, folk music from Peru, New Guinea, and Senegal. The record's cover is a diagram showing how to play it and where Earth is, marked using the positions of 14 pulsars, cosmic lighthouses whose blink rate works like a timestamp. Even the diagram's clock isn't measured in seconds. It's built on a single tick of the hydrogen atom, the most common element in the universe, so that any civilization advanced enough to find the record would already recognize the unit being used. Here's what almost nobody explains clearly. This was never meant as a message anyone would actually receive. In roughly 40,000 years, Voyager 1 will pass within about 1.7 light years of a star called Gliese 445. Not because that star is close now, but because of how both objects happen to be moving. Sagan himself said it plainly: the record would only ever be found and played if there are spacefaring civilizations out there in interstellar space to find it. He wasn't being modest. He knew exactly how unlikely that was. It is, functionally, a message in a bottle, thrown into an ocean with no shore for 40,000 years. There's a story that gets repeated a lot, that the Beatles' Here Comes the Sun was blocked from the record over a copyright dispute. The record's own music producer has said that's not true. The song was never seriously being considered in the first place. What's real is stranger than the rumour. A committee of a handful of people, working in 1977, decided what would represent every human being who has ever lived, to anyone who might someday find it. That record is still bolted to the outside of Voyager 1, right now, 15 billion miles from the people who made it. Nobody has played that exact record since the day it launched. Only test copies, kept on the ground, have ever actually been listened to. But before Voyager 1 carried that record into the dark for good, it did one more thing for the people back home. It looked back. Chapter 6. The photograph Sagan had to fight for. By 1990, Voyager 1's planetary mission had been over for almost a decade. Its cameras were about to be shut off for good to save power. Carl Sagan had one request left. He wanted the spacecraft to turn back and take one picture of home. NASA's own engineers pushed back for years, worried about pointing the camera anywhere near the sun. It took 8 years and 6 separate requests before Sagan got his answer. On February 14th, 1990, from about 3.7 billion miles away, Voyager 1 turned its camera back toward the inner solar system and took 60 pictures, forming what NASA called the family portrait. Neptune, Uranus, Saturn, Jupiter, Venus, and Earth. Mercury, Mars, and Pluto were simply too faint or too close to the sun's glare to show up at all. In one of those frames sits Earth, less than a single pixel wide. There's a stripe of light running through the frame, and people often assume that's sunlight falling on Earth. It isn't. It's scattered light bouncing around inside the camera itself from shooting this close to the sun. Earth just happened to land inside it. A coincidence turned it into the most famous photograph of Earth ever taken. This wasn't the first photograph of Earth from space. That goes back to the 1940s. It was the first time humanity had ever seen itself from the edge of its own solar system. Sagan later wrote the words that made the photo famous, his own exact sentence. "Look again at that dot. That's here. That's home. That's us." On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Every saint and sinner in the history of our species lived there on a mote of dust, suspended in a sunbeam. With that photo taken, Voyager 1's cameras went dark, permanently, to save what little power was left for the journey still ahead. Chapter 7. The edge that isn't an edge. For decades after the photograph, both spacecraft kept flying outward, past the planets, past anything the sun's light could meaningfully reach, toward a boundary nobody had ever actually measured. It's called the heliopause, the place where the pressure of the sun's own solar wind finally gives out against the pressure of the wider galaxy. There is no wall out there, no line to see, no camera could have caught it, because Voyager 1's cameras were already off. So NASA measured it a different way. Voyager 1's instruments detected a sudden jump in the density of charged particles around the spacecraft, triggered by a burst of activity from the sun that let the plasma wave instrument essentially hear the difference. That crossing happened on August 25th, 2012, about 11 billion miles from the sun. NASA didn't announce it until over a year later, once the data was fully confirmed. Voyager 2 crossed its own version of that same boundary on November 5th, 2018, and this time its plasma instrument was still working, so the confirmation came almost immediately. Every headline called this leaving the solar system. That's not quite right, and it matters. Both spacecraft are still gravitationally bound to the sun. They're still inside the outer edge of the Oort cloud, the sun's own sphere of influence, which they won't even reach for another 300 years and won't fully clear for another 30,000. They crossed into interstellar space. They didn't leave home. NASA had already sent two other spacecraft out ahead of them, Pioneer 10 and 11, in the early 1970s. Both went silent years ago, one in 1995, the other in 2003. Both Voyagers have already outlasted every other deep space mission NASA has ever flown. And in 2026, they're still not done. Two machines built for a 5-year trip to two planets had just become the only human-made objects ever confirmed to be traveling through the space between stars. None of these discoveries would ever reach us at all without something built specifically to listen this far. NASA calls it the Deep Space Network, giant dish antennas grouped into 3 complexes, one in California, one in Spain, one in Australia, spaced out across the globe. That spacing isn't decorative. As the Earth spins underneath both spacecraft, at least one of those 3 complexes always has a clear line of sight, so the connection never actually has to break. By the time Voyager 1's signal reaches one of those dishes today, it has already been traveling, non-stop, for more than 22 hours. Every command NASA has ever sent this mission, and every answer that ever came back rode on that same network of dishes, built decades before anyone could guess where this would end up. And still, every single day, they kept sending data home, until one day, in 2023, one of them stopped making sense. Chapter 8, the glitch nobody alive could fully explain. On November 14th, 2023, Voyager 1 started sending back data that made no sense. Not silence. Something worse. A signal, arriving on schedule, that was just noise. For 5 months, that's all anyone on Earth got. Repeating gibberish from a spacecraft that was clearly still alive, but couldn't say anything that meant anything. Engineers eventually traced it to one failed computer chip inside the flight data subsystem, holding roughly 3% of that system's memory, including code the spacecraft actually needed to run. Nobody knows exactly why it failed. Maybe it simply wore out after 46 years. Maybe a single particle of cosmic radiation hit exactly the wrong spot. You cannot send a repair technician 15 billion miles. You cannot even send a replacement part. Whatever fixed this had to be a fix made entirely of new instructions sent over the radio. Voyager's project manager, Suzanne Dodd, put the real problem into words that stuck with a lot of people. The people that built the spacecraft are not alive anymore. There was no living engineer left to just call up and ask. Dodd described the process bluntly as an archaeology dig, hunting through decades-old paper documentation that had never been digitized. Their solution was almost absurdly simple, once someone thought of it. They couldn't fix the broken chip, so they split the code that used to live there into smaller pieces and hid those pieces in other parts of memory that still worked, rewriting every reference so the program would still run as one piece. On April 18th, 2024, engineers sent up the first relocated block of code. Each command took over 22 hours just to arrive. Then they had to wait again, just as long, for any answer at all. On April 20th, 2024, the answer came back. Usable, readable engineering data for the first time in 5 months. By June of that year, full science data was flowing again from every instrument that was still switched on. A team that had never met the engineers who wrote the original code had just repaired a 1970s computer from 15 billion miles away using nothing but patience and 44-hour round trips. It was a genuine reprieve, but it didn't touch the one problem nobody can ever patch with new code. Chapter 9, the slow goodbye. The power problem was never a malfunction. It was always the plan, working exactly as physics predicted it would. Both spacecraft's plutonium generators lose roughly 4 watts of output every single year, permanently. By late 2023, Voyager 1 was down to about 225 watts, less than half of what it had at launch. There is no fix for that. There is only rationing. None of this is sentimental. The instruments still switched on are still returning real data nothing else in existence can collect, direct measurements of the magnetic fields and particles of interstellar space itself. That's the actual reason engineers are fighting this hard over every last watt, not nostalgia. Science that, right now, only these 2 machines can still do. So, one instrument at a time, NASA has been permanently switching parts of both spacecraft off on purpose to keep something, anything, alive a little longer. Voyager 1's cosmic ray subsystem went dark on February 25th, 2025. Voyager 2's low-energy charged particle instrument went dark a month later on March 24th. Then, on April 17th, 2026, Voyager 1's own low-energy charged particle instrument went dark too. It had run almost continuously since launch in 1977. 49 straight years gone in one command. Voyager 1 is now down to just 2 working instruments, a magnetometer and the plasma wave subsystem that first heard the boundary of interstellar space back in 2012. On February 27, 2026, a routine roll maneuver caused a power dip that nearly tripped Voyager 1's own undervoltage protection, the safety system that shuts things down automatically before the spacecraft loses power completely. It didn't trip, but it was close enough that it changed how urgently engineers were treating the power problem. So this year, engineers tried something they'd never risked before, on a spacecraft this fragile. Internally, they call it the Big Bang maneuver. Instead of just shutting an instrument off, they swapped groups of powered components for lower power alternatives all at once, while keeping the spacecraft just warm enough to keep working. They tested it on Voyager 2 first, in July of 2026. It worked. NASA confirmed it in early August. The maneuver bought Voyager 2's 3 remaining instruments roughly 1 more year of life. Without it, another one would have gone dark before the end of this year. A test of the same trick on Voyager 1 in late July also went smoothly, according to the mission's own manager, Kareem Badruddin. There's even a real chance the instrument shut off in April could be switched back on if the fix holds. That has never happened before in this mission. Power has only ever gone one direction. None of this changes where this ends. It only changes when. NASA's own current estimate is that at least 1 instrument on each spacecraft can keep running into the 2030s. Even after every science instrument finally goes dark, NASA believes a bare engineering signal, no data, just a heartbeat, could keep reaching Earth's antennas until around 2036. After that, both spacecraft keep flying anyway, silent forever, in their own independent orbit around the center of the Milky Way, once every roughly 225 million years. NASA's own words for it. They will wander the galaxy for billions of years, longer than our own sun has left to burn. Still carrying that gold record, still carrying Andrewian's heartbeat, long after everyone who built them, loved them, or listened to them is gone. There's one more real thing Voyager 1 left behind, and you can actually listen to it yourself. That plasma wave instrument, the same one that first detected the crossing into interstellar space in 2012, wasn't built to record sound. Space is a vacuum. There's nothing for sound to travel through. But it does measure oscillations in the plasma around the spacecraft, vibrations that NASA can shift into the range of human hearing, the same way you'd slow down a bat call so people can hear it. NASA released that recording publicly under a plain, honest title, Voyager Captures Sounds of Interstellar Space. It isn't music, it's data made audible. An eerie, rising drone recorded 15 billion miles from every sound that has ever been heard by a human ear. Ed Stone took this job in 1972 and never really left it for 50 years. He never got to see it end either. Nobody has yet. What stays with me about this story isn't the distance, it's the decision. Nobody is choosing to let Voyager die by accident. Every single shutdown is a person in a room on Earth deciding exactly which part of a 49-year-old machine gets to keep talking and which part goes quiet first. It was built to last 5 years. Nobody who designed it is still running the mission. Almost nobody who built it is still alive. And it is still, right now, tonight, sending something home. Someday, the signal stops for good. Nobody knows the exact date, but the record keeps flying, whether or not anyone is left listening. If a machine built for 5 years, still running after 49, doesn't sound strange enough, wait until you see the star astronomers just found orbiting Betelgeuse, hidden in plain sight for over a century. Subscribe to Mindwired. If any of this messed with your head a little, well, that's exactly the point. And it only happens because people like you keep showing up. And
hit subscribe right now, Flynn. It costs you nothing, and it's the entire reason Mindwired keeps making videos like this. Subscribe.